Hello and welcome. This is a walkthrough video for the Simple-V Scalar Vectorization system for Power ISO. What we're going to do here is go over the web pages that have been set up so that people have a good idea of what's involved, and it's not really overwhelming. So the first thing to appreciate is that Simple-V is it's a scalable vector system based on ultimately and originally on the Cray vector system, which is actually still in production from NEC through the SX Aurora thing. That ISA it was strictly inspired by the Cray supercomputers, and has been in production ever since. More recently, we've got RISC-V, which is credited for reviving the scalable vectors concept, and there are actually others. It's slightly different. There's Mitch Alsop's VVM extension for what he calls MyISA 66000. That's also it's a different style of vector system. And so first section, what we've got is an overview of the differences of the features. The comparative instruction count is particularly telling. Whilst AVX 512 and SVE2 are getting on for 10,000 instructions each, SVP64, which is the encoding 64-bit encoding, prefixed encoding for SV, is 5. And the reason for that is because we literally take the RISC principle to an extreme. It's a uniform, that prefix, it's a 24-bit prefix that is uniformly applied to embed the scalar 32-bit instructions. We literally do not add a one single vector opcode at all, which has some really quite startling implications. But there's 24 bits of prefix context applied to that, which is a heck of a lot to use to augment that scalar instruction. So that's explained in the overview page. All of that is explained in the overview page. So it goes into a bit of an introduction about where SIMD went wrong, and the article "SIMD known to be harmful" is massively understated, shall we say. It's from a perspective of, it's very well written from a perspective of using a MIPS and then AVX2 and a hypothetical RISC-V 32 processor with this 64 entry vector looping, but that's scalable so up to 64. Whereas the harm that's caused by SIMD is that it is fixed to 2, fixed at 4, fixed at 8, fixed at whatever, but it's a power of 2. And when there's no predication on top of that, that's where the brown stuff hits the spinning bladed devices, if you've seen the Mythbusters episode on that one. The important thing is that this article drastically understates the harm that's caused and the damage that's caused by SIMD. I mean, if you look at if you compile anything with AVX512 now on and look at the assembly listing, it's a shock. It's a real shock. So this overview page is a good start, which first explains about the fact that it's a for loop sitting on top of the scalar register file. Then expands that for you to show that actually you can mark register A, register B, and register T, RA, RB, RT, and RC independently as whether they're scalar or vector, and shows you some code on how to do that. Explains that how predication is then added. Again, none of this is done with modifying the scalar instruction. The scalar instruction is embedded in this pseudocode line here. At the predication, you've gone from that simple loop here to adding more and more concepts. So each concept introduced one at a time. Now you've added predication, and that tests one bit of the predicate mask, which in the 24 prefix you can say what that predicate is. Then there is a concept of element with overrides. So like MMX, x86 MMX, where the floating point registers could be subdivided into integer 64, 2 times 32, 4 times 16, or 8 times 8. You can do the same thing, and that's explained in the structure is explained as in C, a type def union. So if you're familiar with C, that's easy to understand. There we go. Nice little diagram showing that thing, etc., etc. You get the idea. So it goes into detail on the different characteristics, building on the previous one. But the thing is that there's really nothing in this that isn't already in. Nothing major that isn't already in some other vector ISA, scalable vector ISA, with a couple of exceptions. One of them is twin predication, another one is data dependent fail on first. So I'll leave that with you, but that's a good page to get good page to get sort of a high level overview of going from a simple concept to something that's introduces the next concept and the next on to the next on in an incremental fashion. Compliancy levels. I've subdivided it down into 4 compliancy levels. They're basically ultra embedded, where there's practically nothing about that. You're relying on the only critical thing is the addition of an SV state SPR and a corresponding SVSRR1. Which, when you have when there's a context switch, an exception, trap, or exception, you must swap SV state at the same time as MSR and CIA, the program counter, because SV state is, as mentioned in the pages, is effectively a sub-program counter. All right, you've got that for loop for I equals 0 to VL minus 1. You need to be able to make that re-entrant as far as exceptions and traps are concerned, and interrupts are concerned. So you need to save SV state because otherwise you'd be executing up to 64 instructions, and you'd have to know your latency on response, interrupt response, will be absolutely atrocious. Then the next level up is embedded mode, which has more capabilities. Things. So basically, and then you've got DSP, where you have to have saturation modes and map reduce iteration, and then you've got 3D advanced supercomputing, which has to have everything. The idea there is to, like the Power ISA 3 compliancy levels, you can implement a subset of subset of Simple-V to give to target your application without being completely overwhelmed on what you have to actually have to implement. We've got an implementation log on planning of what we've been doing. The other one, there is just the packet format. Well, I'll call it packet format, but it's actually the encoding format, where SVP64 sits, which is in the, bear in mind this is all draft. Okay, the pages all say draft. Okay, we are proposing to take up the 25% of the EXT001 space here. This ensures that we don't have to take up an entire opcode, major opcode, for doing it. We could have proposed it would be much easier all round for us if we'd taken up 50% of that space, which is technically possible to do by using, say, for example, this row here and this row here to give an extra bit, and that would have made a job a hell of a lot easier. But I think that would be a bit excessive. So having worked out how to fit into 24 bits into that the EXT001 64 prefix space, would then go into subdividing those and describing what they are. So we've got element width overrides. We have a mode and execution mask. This is for predicate masks, and there's a subvector length sub-VL as well. If you're familiar with 3D GPU instruction sets, subvectors is basically vec2, vec3, vec4, and you can apply swizzle on top of them for ARGB, XYZW for quaternions, and a whole stack of other things. And it's a major part. Swizzle is a major part of 3D GPU and CUDA workloads. 10%, over 10% of instructions in 3D shader binaries involve Swizzle. So I'll leave that with you. It's very sparse. This the actual encoding page. It doesn't describe any of the actual concepts. It just describes the bit format of the encoding. So it gives no context whatsoever, which is the reason why that overview page was created. So that you've got some sort of handle on it. Now, followed by that is the appendix. Okay, which gives some explanations and of what the heck's going on when you actually get to implement things. What do these encodings mean? I think now for anyone reading this and going, "Oh my God, this is just ridiculous," and is freaking out right now, I have to say that the first time that I looked at the Power ISA 1,300 page document, my heart sank. It was 6 months before I understood why the Power ISA was so large. It took 8 months to for the right brain thought patterns. No, longer than that. For the MSB0 for putting the least significant bit in the highest numbered number, it took, I think, somewhere around 15 months for an automatic translation in my brain of, oh, I'm looking at a numbering 0 to 31. The most significant bit is number 0. There's literally 15 months for my brain to wire that, and that's just on the scalar ISA alone. Please do not be surprised if the same thing happens to you when looking at Simple-V and SVB64 itself. All right. It's just, you have to bear in mind that we've been developing this for almost 4 years, and it takes into consideration aspects from scalable vector ISAs that date back 30, almost 40 years. So just be patient, please. Be patient with yourself. And patient with us as well. There are a lot of concepts that are just not present in a scalar ISA, not present in a packed SIMD ISA as well. So if you are familiar with VSX, it won't help you. Okay. We found everybody who has SIMD experience is actually hindered because they believe that it should be much more complex to work with when you actually get to writing assembler, and it really isn't. We're literally cutting we consistently found that when you implement programs in SVB64 assembler, it is a massive reduction. I mean massive, an order of 5 to 20 times smaller programs in assembler. For the same job if you did it in packed SIMD or scalar. It's astonishing. The reduction. So let's move on. The appendix again. It gives a bit more detailed examples into the concepts where the packet format simply names the opcode format names the modes. The appendix actually describes them, and it gives some pseudocode to indicate what they are. Fail on first is a particularly crucial one. There is a paper by ARM were first to add load store fail on first. RISC-V vectors have also added it. They've named it something differently, but it basically allows you to speculatively load a sequence of elements, and the load store engine is allowed to truncate the scalable vector length to an amount that will succeed. And it means that on page boundaries, you don't end up causing a page fault. The next time you go around the loop, there will be a page fault, but not crossing the the batch of loads that have been done. Everything. It's an extremely smart idea that saves an astounding amount of assembler. If you have a look at the patch for Stringer copy that was submitted a couple of years ago for packed SIMD VSX, it's 240 lines of handcrafted assembler. An equivalent RISC-V Stringer copy, which is more powerful because you can do up to 64. In SVP64, you can go up to 64 load elements, and far more than that with RISC-V. It's 14 assembly instructions. 14 versus 240. Right. Even the ARM implementation of Stringer copy with SVE2 is something like 30 or 40. So it's an astonishing, like I said, it's an astonishing reduction in the thing. But you need to read the academic paper by ARM just from this one paragraph here. The background context for that one paragraph is an entire academic paper by ARM on fail first. So you just need to bear in mind there is a hell of a lot here, right? I then extended that to that concept, something called data dependent fail first, where you can actually, like a branch conditional, you can actually truncate the loop based on a bit test of similar to a branch conditional, the BO field, and end the loop based on truncate the loop based on basically it turns every single instruction into a compile, which ends the loop at that point. So if you've got something which has got saturation, that you didn't want to have to, within a tight inner loop, do a test for saturation, you can actually get the operation to truncate at the point at which the saturation fails in your sequence of audio or video data, or other data, deal with the loop, and then outside the tight inner loop, detect the conditions as to whether there was a failure and act accordingly. So it's about saving instruction count and getting increasing performance. It's just I just there's a lot of thought gone into this. Right. So there's a bit explaining about how condition registers, which have been extended to 128 condition register fields, and then we use those as predicate masks. The condition register fields as predicate masks. So that took a bit of quirky explaining and things. We're saying assembly notation, parallel reduction algorithm is currently in development. How do element width overrides work? Twin results, because like in when you have a RT pair, like in load quad, you're going to have an RT pair, or in store code you're going to have an RS pair. When you vectorize those, what happens? How do you treat the upper and lower entries of the pair? And what we decided to do is expand them out, so there's actually two separate vectors, one starting at RT and one starting at RT plus max VL. When max VL is set statically, read the set VL instruction thing. This is with pages intended as an overview here, not a detailed thing. Quirks. So we describe the rules which are based on these what I've called around fundamental and violate RISC principles. The prefix does not impinge on the suffix. The suffix which contains the 32-bit instruction is not changed. Fundamentally, it's encoding the actual opcodes. You don't go, oh, this is prefix, therefore we're going to reinterpret the scalar instruction as something completely different encoding. No, it is definitely 100% in all cases. It is, when it's embedded, it is a 32-bit encoding, exactly as in the Power ISA 3 right now. We did actually make an attempt to give different meanings to the bits. It went really badly. It wasn't fun, but I did it deliberately so that I could experience it. I think it's Hindu religion or Buddhism. Explore that space. I explored that space. I don't want to do it again. So we stick to a strict and fundamental inviolable RISC principle. You do not have different encodings of the scalar embedded, the suffix, just because it's embedded in the prefix. But we do have some different, I call them semantic caveats. For example, when you set element width equals 8, then an add with carry becomes an 8-bit add with carry, producing a 9th bit carry out, not a 65th bit. Yeah. So it doesn't change the actual scalar encoding of the add with carry instruction, but it semantically changes the meaning. The element width override changes semantically the meaning, but everything else is pre or post pre-augmentation, post-augmentation, or post-analysis. And the reason why there's these this entire quirk page is because one of the exceptions to that rule, the only exception to that rule, is branch conditional. Okay, where branch conditional in 3D GPUs, you need to be able to test a batch of predicates, a predicate mask, as whether it's all ones or all zeros, and skip over instructions, because if the predicate mask is all zeros, well, then every single predicated instruction is a no-op, and you'd be wasting your time even sending that to the ALUs. Nothing would happen. So to help with that, you used to branch over the instruction that's going to be that, if that predicate mask is 0, you know for a fact that it's going to be you need to branch over it in order not to waste CPU cycles. So we had to actually create almost a variant, extend the branch conditional pseudocode and replace it with something. But it's literally the only time that the scalar instruction deviates from its when it's prefixed. Okay. Again, I was explaining a bit more about the fail first modes. That it's not a violation of the rules, but it's quirky enough to actually be mentioned in this page. Saturation. Again, saturation is applicable as a uniform concept on top of instructions that were not originally designed to be saturated. So that's every single thing which can produce an arithmetic result. It can have a saturation mode applied to it, and so this avoids. Again, it's a perfectly reasonable thing to do to abstract out the concept of saturation from the from instructions, so that you avoid having to create an add and a saturated add and an unsaturated add. And those were 64-bit, and then well, we need a 32-bit version as well, and we need a 16-bit version of that as well, because we need an 8-bit version. Oh, we need a SIMD version of that as well. So we need a 60-foot. That's where the SIMD hell comes in. No, just have a mode in the prefix. The results are saturated. It's a RISC principle. Of those 24 bits, 5 of the bits are used for a mode. One of those modes is saturation in general on top of the scalar instruction. It's really that simple. Another one is you can see all those things. Another one is a floating point single we redefined to become half of the width, half of the element's width. So f add s, when you specify an element width of 32, takes the concept of FP64 being used to store an FP32 spread out across the FP64's bits. So it's an FP32 number stored in an FP64 format. When you do sv.fadds element width equals 32, it actually stores an FP16 spread out across the 32 bits in FP232 format. And so when you see an S on the end of instruction, instead of thinking, oh, that's 32-bit in a 64-bit format, it's important to think, oh, that's half of the element's width. Again, for 3D GPUs and some DSP audio and video processing, you've got Swizzle and Unpack, which again are worth a special mention. So that, just to be aware what that page is. Yes, it's a RISC paradigm, but you just have to think about it and think about how that paradigm fits when you have all of the concepts and the modes that come with this type of optimized efficient ISA. Now, this page takes a bit of explaining. In the Power ISA, you have let me grab this. So, let me find the thing. Open Power ISA. Let me find a page tree. Open Power ISA tables. Nope. ISA. Right. Let's look at fixed arithmetic. Okay, so you'll recognize this as being the Power ISA pseudocode extracted from the PDF by hand. Psi. This is add immediate, for example. But what's missing from this is how that is then interpreted. How that is augmented. How those fields are augmented. When it comes to when it's embedded as a prefix in SVP64, and there we go. Add I. There we go. Oh no, it's add IC. So we had to go through and classify all of these instructions as they're in their format, and for when it comes to interpreting and augmenting the fields, particularly what mode is it single predicated? Is it twin predicated? Um, uh, 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 how do we add? How do we extend the register field numbers RA and RB and RT to 128 bit? And this encoding 1R, 1W, 1 read, 1 write immediate, that is we had to go through an entire instruction set, adding in the SVP64 equivalent of the fact that it is the instruction is deform or whatever. So it says here in the specification, it says in the power ICE of 3 spec, it says add I is deform. It is also SVP64 1R 1W immediate form, actually RM 2P 1S 1D form, because it's twin predicated. There is one source and there is one destination, which if you look at this, it's got one source and one destination. So that very interestingly, that was an automated process of looking at the register profile for each instruction. And there's a piece of software which does that automated thing, so adding new instructions is easy to do. So it's got all of them, all of the instructions with the different formats. Single predicated, 2 source, 1 destination, RLWIMI, right? And so on and so forth. SPRs, there's a list of special purpose registers needed, which include SV state, SVSRR1, a remap, and 4 SV shape SPRs. SV state, so that again, that describes their format. What's that image there now? Let's look at that page later. Then, as mentioned in the quirks page, there are different modes. There's an arithmetic and logical mode, branches, load, store, and condition register operations. So these are worthwhile going over for things. So, for example, have a look at the one for normal or arithmetic. Again, here now finally we're getting down to some detail of the different modes. We've got a normal straight vectorization mode. You've got fail first or data dependent fail first mode, saturation mode, a reduction mode, all vector ICEs, scalable vector ICEs, and many SIMD ICEs have reduction. It's added as a mode, and it's quite interesting. It's a slight misnomer in the in SVP64. It's in Simple-V Scalar Vector Vectors. I won't go into details. I'll leave it to go over. It's quite interesting because we've managed to combine both iteration. So you can do a Fibonacci series with the same instruction just by changing the relationship between the source and destination registers. You can also do reduction. You can do sum. You set the if you have a 3 in 1 out instruction, like multiply and accumulate. You set the accumulator equal to a scalar, and if you apply a reduction, the reduce mode, if you switch on the map reduce mode with the vector on the inputs, then you get a cumulative sum. I mean, it's really sort of startling that the way that it works to produce things that in other instruction sets, you have to add explicit opcodes for these things, and we've just abstracted all of these things out on top of the base element, including map reduced iteration and things that you only really see in NEC, SX, Aurora, and RISC-V RVV. Again, a bit more about the different modes. Predicate result is a particularly interesting one. The reason why, as I mentioned, is mentioned in the quirks page. When let's have a look and see everything. Instruction groups, things like load and store deals with. So whilst those normal mode, the arithmetic one, you're dealing with, you can augment it to make things saturated. You can add this and that, the other, but element width. If you've got a 4-bit condition register field, how can you make its element width equal to 8? Yeah, makes no sense. How can you have saturation on a branch? It doesn't even return an arithmetic result. Yeah. So what that means is that it turns out that those bits which are dedicated in arithmetic to a mode to augment for arithmetic purposes, we could do something completely different with those bits for branches. You can do different things with those bits for condition register operations, likewise for load store. And I'm currently in the process of including a pack and unpack mode, so that you can apply VPack and VUnpack VSX concepts, an abstracted concept, to move operations, arithmetic operations, even to load and store, which gets very interesting. So it means that we'll be able to directly pack and unpack from a load without having to load it into register first and then do the VPack or VUnpack waste register file, so encoding space to do it. So it's just to give you some idea. This is not just about designing something because it's fun, although it is. There is actually genuine reasons why these things are added to save on resources. In some cases, dramatically save on resources. So finally, then we've got the core SVP60 instructions themselves. SetVL is the one that people will who are familiar with Cray-style vectors, the original Cray, ISA, NEC, SX, Aurora, and RISC-V RVV. You will be familiar with the existence of a SetVL instruction, and this is the page that describes it. Now I've added something of vertical first mode, which I won't go into on this one, but it's basically, I won't go into detail, but basically where horizontal mode, you go on the vector for loop from 0 to VL minus 1 before moving on to instruction. In vertical first mode, you go down the instructions and you have an explicit instruction SV step, which moves on to the next element, and then you do a branch conditional back to your loop. Mitch Opsup's My ISA 6600 VVM is specifically has vertical first mode embedded in it, and it is an extraordinarily powerful concept, which can be implemented in a very simple hardware. You don't actually have to have complex microarchitecture at all. Then the SV step instruction, I'm still on the to-do list on that one, and remap. Remap it's an advanced form of vector structure packing, and it's extraordinarily powerful. It takes some of the common loops for computationally heavy arithmetic and just implements them in hardware. So you have some setup instructions, and then you have in some cases for matrix multiply, you have one instruction that's multiply and accumulate, and that's it. So you set up the vectors, set up the instruction, do the multiply and accumulate instruction, and you literally cover in place an entire matrix multiply of something like 5 by 3 times 3 by 4, 2 by 3 times 3 by 2 to produce a 3 by 3 result, etc., etc. There's no limit. There is no artificial limit in the matrix multiply schedules based on powers of 2, because it's scalable vectors. We're abstracted out from power 2 from SIMD. So all that's gone. So there's no more of this data hardware unrolling to roll the data around to make it go into the SIMD things, and yeah, just it's 3 instructions and that's it. FFT DCT, this is normally only seen in high-end DSPs like the Texas Instruments MSP 430 series and the Qualcomm Hexagon DSPs. Those are both VLIW processors. This is a standard scalar symmetric multiprocessing system. Is not VLIW. You can do multi-issue out of order execution. You can do in order if you really want to, etc., etc. The only caveat on FFT DCT is that it's limited with power 2 radix. But anyone familiar with FFT and DCT knows that you can combine. You can you can take 2 FFTs, one of 2 different types of sizes, and combine them to do a convolution on top of them to create non-power of 2 radixes. But the number of instructions needed to do those power 2 radixes is drastically reduced. And then there's what's called an indexing mode, which is it's anyone familiar with a thing. I'm going to quote a bit of pseudocode at you. GPR brackets RT equals GPR brackets GPR brackets RA brackets. And once you understand that if you think that through in a scalar ISA, it's absolute hell. But in a vector ISA, it's very, very much more simple and straightforward. So we've had to come up with an indexing system, which has introduced a 5th instruction to to Simple-V, SV index. It's currently under development. So that is really it. You can effectively end exploration of Simple-V SVV64 there. However, having made a study of the Power ISA for over 2 years now, we noticed that good as it is and based on supercomputing principles, which I mean it's astounding. We did, however, notice that the primary focus has been on the PAC-SIMD ISA. The majority of the advances have been in that, and it's kind of we perfectly understand that it's it's been IBM has been the main contributor and has basically targeted their customers. their customers' needs and focused on the customers are there for the kinds of workloads that they do. But it rather unfortunately it means that the rest of the ISA, particularly the scalar part, is a little anemic. And for example, let me have a look. Big integer operations. There is no equivalent to the Intel addx instruction, which is where you take a two 64-bit quantity, multiply them together, and store them across an RT pair. That was added in 2012 to the Intel x86 instruction set. But no equivalent was added to the Power ISA. I don't think even the VSX instruction set has one. It's got a 128-bit multiplier and 128 thing, but there's no 64 times 64 to pair of register split, high and low. The assumption is that you would use the MAD HDU and MAD LD to do a pair of instructions, and that becomes very awkward when you're doing tight inner loops of applying and you want to apply horizontal vector onto a single instruction. And what we worked out was that you can actually, if you've got this instruction, which is a multiply and accumulate pair, producing a pair, and you apply the implicit register, that thing I mentioned about RT and RT plus maxPL, you can do a big integer math. It becomes the basis of multiplying a scalar by an arbitrary length, a scalar register A by an arbitrary length big integer register B, and then you just have in your assembly code you have a loop around that, which completes the entire algorithm D from Knuth. That's real. It's it's quite simple, but that without that instruction, it's a lot of work. If that instruction was not added, then it actually damages the Power ISA from being it compromises its performance when it's given a big integer math workload. So all these instructions, we specifically propose them to be added as scalar instructions, and have gone to a lot of trouble to provide justifications as to why those should be added on their own merit as scalar instructions to improve the scalar Power ISA for the benefit of improving the reach of the open power instruction set. And then it happens to be benefits if they're vectorized with SVP64 as well. But it's really important, crucial to appreciate that there is this delineation, there is this ending point of between here, which covers the scalable vectors system, and here on these scalar instructions, which are proposing in addition. It includes things like floating point move between FPR and GPR, which is a classic case because these used to be in the Power ISA for I don't know how long ago. I think it was Power 6 or something like that. IBM Power 6 had these instructions. They were removed. And the reason why they were removed was because they're all present in VSX. And if they're present in VSX, why do you need them in the scalar instruction set? But now with the we've got the compliancy levels power ISO compliancy levels, SFS, which is the fixed scalar fixed point, and SFFS, which is a scalar fixed and floating point. We're not intending to implement VSX at all. Or we might implement the 128-bit single, the quad precision floating point. But that's sort of just a whole new thing. We've got enough to do as it is on a thing. But with those instructions missing, you'd need to add VSX and the VSX registers and the state and things. It's just like, no, we're not doing it. So what we're doing is we're proposing some scalar instructions, taking the opportunity to add a float load immediate, which there'll be two halves to that. One is the BF16 is then can be expanded out to 64-bit, but then there's a second instruction added as well, which gives you another 16 bits, which is dropped into the remaining the lower parts of the FP32 to make the number a full FP32, of course stored as usual in the FE64 format within the floating point register. And there is somewhere I have a note saying that if somebody wanted to prefix those, there is some recommendations on that. Where is it? Might be worthwhile to extend these two instructions to v3.1 prefixed pfmovis and pfrlsi. So you'd actually use part of the prefix space to do a full FP32 immediate, and the follow-up instruction provides the missing exponent bits and the lower mantissa bits, so you can load a full FP64 immediate into prefixed instructions. That even just having this one instruction, the BF16 immediate, which gets expanded out to FP64, the amount of effort that it is needed to do a floating point load at the moment is just ridiculous, and it's in even for things like loading 0.0 into a register. You can't do it into an FPR. You cannot do it. So you have to go through a load store, and think, it's a lot of hassle. And 3D shader binaries, even the MP3 uses floating point, and you can't load a 0 into the register for doing multiply and accumulate. So then also we're taking the opportunity to add Java semantics and JavaScript semantics to the conversion, floating point conversion. JavaScript 1 is absolutely awful. We've got some assembly code here somewhere. Whoops. Sorry. Come on, you can do it. Oh, sigh. There we go. It's 35 instructions with 6 branches to do a floating point to integer conversion in JavaScript. It's mental. And it's because they do this power of 2 coding. Power of 2 encoding. Here we go. And, there. So this gives you an idea of how many instructions. If you do these conversions in assembly code, it's awful. Right, so here's how in C++, you do that conversion, right? And that's for the instructions that you end up. I mean, that's mental. To implementation of JavaScript to int32. So, as I said, it's about a thing, and ARM has this instruction, this JavaScript rounding instruction. It means, for people using Power ISA for web browsing, you have a massive performance kick in the pants. So when I said JavaScript browsing, the whole focus, we're keenly aware that IBM's primary focus has been on server market. Everything that we've been doing for the past 4 years is about kicking the Power ISA into a much wider market, mass volume use, putting it back on par where it used to be when Apple produced PowerPC processors, because those were mostly, those were all 32-bit was a long time ago. There's a lot of catch up to do, and with the reintroduction of Cray-style vectors now as something that is not the sole exclusive realm of supercomputing. So people have realized that Cray-style vectors save power even in embedded environments, embedded scenarios. Because you can do that vector for loop, use far less instructions. You spam the back end of your pipelines in your embedded or your finite state machines in your embedded core, and the issue and decode phase sits idle, twiddling its thumbs. The programs are smaller. The amount of work that the level 1 instruction cache is doing and the decode and issue phase is less, so you end up saving power. Smaller programs in embedded scenarios is really important, especially mass volume products. So it's been sort of a realization that scalable vector is actually really important, and would very much like to see the scalable vectors come to what is already a supercomputing class instruction set known as the Power ISA. And there are good ways to do that, and there are some really bad ones. And I have to say, it takes a lot of time to understand the difference. There is a hell of a lot to study to do a full comparative study, and that Sigart considered harmful article gives you a glimpse in that. But I have a specific page in here, a vector ISA comparison, which goes into a classification of what SIMD ISAs are commonly mistaken for vectors, some actual 3D GPU ISAs, architectures and ISAs. All of them are SIMD, absolutely every single one. They mention the word vector. They don't have any scalable vectors at all in any of the 3D GPUs. Absolutely not one single one of them is a true vector ISA. And then there's this last section which contains the instruction set, which are actual scalable vector processor architectures and ISAs. So that's it. That's it really. I've gone pretty much everything. It's quite a lot because there is quite a lot. Anyone reading this, I need to impress on you quite how much is involved in vector ISAs. The RISC-V Foundation has been developing RVV for over 6 years. There was a lot of work gone into it prior to its even the announcement of RISC-V, because the founders have studied Cray-style vectors for several decades. Lots of people from Northrop Grumman came out of the woodwork to help with RISC-V vectors, because they remembered actually using the Cray-Star supercomputers, and realized that the importance of reviving the concept. But ARM, bless them, they've done a predicated SIMD. It is not the scaling. I mentioned this in that page. The scaling is a parameter that can be chosen by the hardware architect rather than the programmer. You can use predicate masks to mask it off, but developers who are used to ARM Neon are really struggling. The other shocking part of ARM SVE2 is that SVE2 is 1,000 instructions, but depends on 1,000 instructions, and it depends on SVE. SVE is around 4,000 instructions, and it critically depends on Neon. Neon SIMD, packed SIMD is around 2,000 instructions and critically depends on the ARM scalar instruction set. So if you want to adopt SVE2, you need to basically convert the entire processor to an ARM core. So it's the same with AVX 512, but that's a closed ISA anyway. So just once you get into the details like this and you understand the depth of the amount of work that's gone into scalable vectors, Simple-V with its uniform RISC paradigm starts to look sane. So I know it looks like a lot of work, but compared to alternatives, it's small. All right, I'll leave it at that. Thank you very much.